Like, I don't know if you realize this yet, but whenever you see it worth, all of this, whatever, that you all have, because it's different. Like my freshman year, when I was like, I had a full group chat of 100 people where it was just, hey guys, there's a tour going to Arnold, or there's a tour going. Moms there now, every time it'd be like white cheddar, bacon burgers, it's like brisket mac and cheese, like just like really class stuff.
Nice.
Gotta try that.
Yeah, you just gotta,
Okay.
yeah, keep an eye on
Yeah.
So we're gonna finish electrical circuits today. We started it last time. It's actually pretty straightforward enough that we could finish in like just yeah, basically two days. So there's a bunch of engineering and physics behind this. You know, the Kirchhoff circuit laws talk about like voltage and the current laws. There's all these mathematical equations that describe voltage drops at all these devices. That combined with the voltage law, the fact that all the voltage drops have to add up to the voltage gain in the circuit, results in a differential equation for the charge in the circuit, Q being the charge in the circuit, that is second order with if you assume L and R and C are constants, constant coefficient, and then the voltage source is like acting like a forcing function, a non-zero forcing function, which makes this in general non-homogeneous. And you can just solve this because we know how to solve these types of equations. So we looked at one example here where we saw that the charge is going to equal this as it evolves, and then the current is this. And I was trying to make sense of like what's going on is initially there's a charge of 2 that grows to 3. So it gains 1 coulomb due to the battery. And then as it gains, it doesn't go beyond 3 because the current actually just stops after infinite time. So it's like if you're trying to look at like what happens long term in this circuit, it'll have gained 3. It'll gain 1 coulomb to increase to 3 coulombs, and then the capacitor only accumulates charge so long as current is still running, and the current also goes away as time goes on. So let's look at another one where we have a circuit so we're always going to start with this equation because this is the basic RLC equation that we derived using the voltage law. So we'll have this, but they'll always give you a bunch of information like about the circuit, like R is 2 ohms, L is 1 Henry and stuff. So let's write that in. But I'm gonna write 2 different equations because you see here the voltage source. This is the E of T, which is on the right-hand side, is a 1-volt battery that shorts out. And shorts out means that it doesn't provide any more electrical potential energy. It doesn't provide any voltage. That means E of T becomes 0 after pi seconds. And then it gives you some initial, like basically it's saying the initial conditions are 0, both the charge and the initial current. Find the charge on the capacitor, and we can also look at the current maybe. But here, I'm going to build 2 equations. One equation for before it shorts out and one for after it shorts out. L is 1, so it's going to be Q double prime. And then R is 2, so it's going to be 2Q prime. And then C is 0.5, but 1 over C is just going to make it become 2 because it's 1 over 0.5. And before it shorts out, my E of T is a 1-volt battery, so it's 1. And this would be like for 0 to pi. So we're just building the equation for before it shorts out. After it shorts out, the devices are all still the same. So it's going to be the same equation. But instead of 1, shorts out, so it's a 0. The voltage is 0 on the battery. So you have two equations for one before it shorts out and one for after it shorts out. So I'll just say this one's for pi t, and then they just want you to model all the way up to 2 pi, so I'll just say 2 pi. So there's that. And what I'll do is I'll solve each of these, right? We'll have to solve them separately. I'll do this like the red one here, and then there's a blue one here for after it shorts out. And then kind of like with our mixtures that we had, I'm going to label the solutions to be like this one is a Q1. From this one, I'll get a solution Q1. And then from this one, I'll get a solution Q2. So let's do Q1. The solution to Q1 requires us to do the characteristic equation. I mean, they're both going to have the same characteristic equation. So this will be the homogeneous solution for both of them because the left-hand side for both of them are the same. And so this is equal to 0. And you have to use a quadratic formula for this because this doesn't factor. So you can check on your own. This will end up becoming -1 plus or minus I. That's not worth doing in front of you, so I'll just say that's what you'll get. Of course, we read off the real and imaginary parts, so alpha is equal to -1, and beta is equal to 1. And we're going to write the homogeneous solution. So we'll just say this gives us our QH is equal to C1 e to the -t, because that's the alpha, cosine of beta t, beta being 1, it's just going to be beta, yeah, so that's that, plus C2 e to the -t sine of t. So that's our homogeneous solution for both of them, actually. Yeah, did I? The t's are both negative?
Like e to the -t.
Oh, because this one's alpha -1.
Oh, okay.
Yeah. Yeah. And this one's positive. So that's your homogeneous, but the red one has a non-zero right-hand side, so you have to build the particular solution for this red equation. So I'll just say for the red equation, the particular solution form would be equal to a constant because it's just equal to 1. So you could just plug that in. And of course, the derivative of a constant and second derivative of a constant are 0. So you just have 2a is equal to 1. And therefore, your a is equal to half. So that's your particular solution for the red one. So we have the general solution for Q1. So I'll just write that as Q1. So I'll say here Q1 is going to equal the particular solution, which is the half. Plus the homogeneous solution, which is this whole thing. So that's the general solution for Q1. But we want to find not just the general solution, but find the C1 and C2. So I'll just say this is just your general solution. General solution because it has still the C1s and C2s in it. But you can apply these initial conditions, right? So the initial conditions are saying that you have initial charge on the capacitor is 0. That's like saying your Q of 0 is equal to 0. Your initial current is equal to 0 as well. So that's giving you the condition that I of 0, which is the same as Q prime of 0, because remember, current is the flow of charge, which is same as derivative, rate of change of charge. So that's equal to 0. So we're going to use those. So the first one is the Q of 0 is equal to 0 condition. And so I'll just write both of them down here, say. And the other condition is, I'll just write the derivative part. So you have these two are the initial conditions. And so we'll have these two that we need to satisfy. This is our Q1. So I know I'm going to have to take the derivative of this eventually. So I'll just move this down and just go ahead and take the derivative of this right now. So Q1 prime, the half goes away, negative C1. Oh, actually, I have to do the product rule. So it's going to be, I'll pull the C1 out because this needs a product rule. And I'll say the derivative of the first is negative e to the negative t, cosine of t. And then the second term is derivative of that is negative sine, so it'd be negative e to the negative t sine of t. Plus, I'll pull out the C2 and then do the product rule between these two is negative e to the negative t sine of t. And then plus e to the negative t cosine of t. Derivative of sine is cosine. We'll eventually need this for this initial condition here. So you have these two initial conditions. I'll just say the first one is saying that your Q1, so maybe I'll even label this as this is my Q1 and Q1 prime is equal to this. So this is saying Q1 is equal to 0 whenever your t's are all equal to 0. The half is there. This is going to be cosine, this is e to the 0 is 1, cosine of 0 is 1, so it's just C1. This goes away because sine of 0 is 0. So that's going to give us immediately that C1 is equal to negative half. And then your derivative 1 is plugging into here. So 0 for the Q prime. You're going to have e of zeros are all 1s. Cosine of 0 is 1. Sine of 0 is 0. So you're just going to have a negative 1 times C1 plus, well, we'll see if it's a plus or not. Okay, so sine is going to be 0. Cosine is 1. Okay, so it's just going to be C2. And if you solve for C2, that's just like moving the C1 to the other side, I guess. So C2 is equal to C1 at this point. And then that's obviously equal to negative 1. So that means that C2, I mean negative half, is equal to negative half. They're both equal to negative. So that gives us our solution, which is going to be our Q1 is this solution right here. So I can copy and paste it. But it's going to be with C1, oops, and C2s being negative half. And negative half. So this is the answer for before it short circuits. This is like for 0 up to pi. This will model the charge in the circuit. Basically the same thing we did before. But now we have it shorting out. It's going to be this blue equation we have to solve. This blue equation, maybe I'll just copy and paste. Let's say this right here is now what we're going to do for after it shorts out. So we have another page here for that. So I'll paste this. This is what we're going to now solve. It's like we've already kind of done it because Well, actually, we literally did do it already because it's basically a homogeneous equation. This is one in the right-hand side, this is 0. So the answer for the blue one is just the homogeneous solution. So it's going to be just this right here. So I'll just paste that in and say that this is literally the solution for Q2. So I'll say Q2 of T will equal just this. But I want to make it clear here that the C1s and C2s that we had for the general solution from the first equation, so the C1 and C2 here, we got was -½ and -½ That's not going to be the same here. So you can't just say, okay, well, now I'm going to just plug in -½ and -½ into C1 and C2. This was for the first part of the equation, first part of this scenario is saying you have an initial, like this is initial charge and initial current. So, and these initial charge and currents are when T is equal to 0. So it only applies to the red equation because the red equation is for T equal to 0 to pi. It has nothing to do with the second equation because the second equation only exists after pi. And so this initial condition is not applicable to this blue one. So the C1s and C2s will not be the same, and we'll have to find them using some other condition. I'm going to differentiate I'm going to make a distinction here. An easy way to, if you're lazy, is I know these C1s and C2s are not the same. If you put tildes on the one of the sets, then it will be an efficient way of noting that they're not going to be necessarily the same. But how do we find the C1s and C2s? So what I'll say here is there is this Q1 and Q2 are your charge in your circuit. There's a charge that's going to evolve due to the battery. For the first 0 to pi seconds, it's going to, it's not going to stay the same. The Q1 will represent the charge in the circuit, and it'll grow probably because the battery is going to cause the circuit and the system to gain charge. So it'll grow, and then it shorts out. So Q2 is probably going to go down after it shorts out. But right at T equals pi, the charge in the circuit shouldn't suddenly disappear or appear all of a sudden. So there has to be continuity. Remember, like with mixtures, you couldn't have like salt suddenly appear or disappear, like conservation of matter. So conservation of charge idea, where it's like you need to make sure that whatever Q1 was equal to at pi has to also be what Q2 was equal to at pi, because then otherwise you'll have a discontinuity in your charge. And so we'll write that as one of the conditions we for sure need to have. Q1 at pi has to equal Q2 at pi, right? When they shorts out, you don't want to have charge suddenly appear or disappear in the circuit. That used to be enough when we had mixture problems, right? With mixture problems, we only needed one condition because it only had one arbitrary constant C in there. So this needs two because this only gives us one condition for two unknowns, C1 and C2. The other thing we're going to assume is that the current doesn't suddenly spike, or, there's no discontinuity in the current. So that means that the current has to be continuous at the moment it short circuits, which is the derivative of charge. So we'll say these are my continuity conditions to ensure that you don't have charge suddenly appear or disappear, or current suddenly appear or disappear right at the moment it short circuits. That's good enough for us to be able to find the two constants C1 and C2 tilde. You don't use the initial conditions. For the initial conditions, you use it for the Q1. This red one uses the initial conditions because this one is for, T0 to pi. But this one is not for T0 to pi, so the initial conditions are irrelevant. That was like in the past, way in the past, So we'll have to pick up from where Q1 left off, basically, to get these C1, C2 tildes. So I know for sure that I'm going to have to take the derivative of this eventually, because there's a Q2 prime pi has to equal Q1 prime equals pi. So let's go ahead and take the derivative of the Q2. So Q2 prime is gonna be, it's gonna have like, basically, it's gonna look like this right here. So I'm just gonna copy and paste it, because we already did it. It's this, it's literally like this right here, because it's like taking the derivative of this blue stuff here. So we kind of already did it, so I'll just paste it, put it right here. The only thing is I'll just make it blue, and then also I'll put tildes on these. Yes.
So we're putting tildes on the C1 and C2 because the C1 and C2 are different from one another, or that pair is different.
That pair, yeah, the C1 and C2 pair for the Q1 solution is not necessarily going to be the same as the C1 and C2 pair in your Q2 solution. So let's, that's the first derivative, that's the derivative of Q2. I know that I'm going to have to, for the second continuity, which is the current is continuous, requires me to set Q2 prime pi equal to Q1 prime. So I'll have to take the prime of Q1, which is like taking the derivative of this right here. And it's literally going to be the same thing as, because we already wrote it here. So I'll just say this right here is Q1 prime of T. So we have, oops. We have this, but back then we had already gotten that C1 and C2 are negative half. So I'll write that in. This is literally just writing this right here again, Q1 prime, but here we already got these. Oh, actually, yeah, C2 is equal to negative half. So we have those. So this is, I'll make it red so that it's consistent with the fact that I colored this one red, up here. So now we have everything we need. So what I'll do is I'll just say that this is the condition that we need to have is these two. So let's look at what these mean, each of these. I'll use colors here again. So Q1, maybe it'd be worth copying Q1 just so that you see what it is from here. So I'll paste it here. So here's Q1. Okay, Q1 pi is like plugging in pi into this. So there's a half. There's a minus 1/2 e to the negative pi cosine of pi. Cosine of pi is -1, right? Because it goes down. So it's going to be plus half e to the negative pi minus half e to the negative pi, but sine of pi is 0. So this goes. So we have that. And this has to equal Q2. Q2 is this sine. Okay, so Q2 is this equation right here. So we'll use blue. I'm plugging in pi into all the t's. Cosine of pi is -1. So it's going to be negative C1 tilde e to the negative pi. Cosine of that. So that's why there's a negative in the front, because cosine of pi is negative. This is going to vanish because sine of pi is 0. So we have this. Let's just solve for C1 tilde, because this equation only has C1 tilde with, there's no C2 tilde, so you should be able to solve for C1 tilde. All I'm going to do is I'm going to just so I can multiply everything by e to the pi, I guess. So then it'll just become this e to the pi will go away, and then you have a negative. So I'll just say it's going to be negative. Okay, C1 tilde is going to equal. I'm going to pull out the half, and then it's going to be a negative, and then I'm going to multiply by e to the pi. So this one will get e to the pi on it. And then this e to the pi and e to the negative pi will cancel, so it just become 1. So this will be your C1. Okay. Now let's look at this one down here. So we're going to plug in Q1 prime, pi into Q1 prime, which is pi into this one, red one. Okay, so you have half. Okay, that we'll worry about. Inside of this, the sign will go away. You just have negative e to the negative pi. Cosine of pi is negative. So you have a negative times a negative times a negative, which is overall a negative. I'll use blue, red. Wait, all right, good. Negative half e to the negative pi. That's this. And then on this one, the sign goes away. Cosine of a pi is -1. There's a negative here, so that's positive half e to the negative pi. That's that equals the blue Q2 prime. I plug in pi into all this. Okay, so cosine of pi is -1. There's a negative. This vanishes, so you'll have C1 tilde e to the negative pi. And then you have this term right here, sine goes away. Cosine of pi is -1 times this would be negative C2 tilde e to the negative pi. Okay. On the left-hand side, these are just subtracting each other. So this will cancel with this. So we'll just have 0 is equal to, I'll factor out an e to the negative pi. And you'll get C1, because they're both negative negative pi, minus C2 tilde. So if this has to be true, there's only one way this will happen is if you have C1 and C2 tildes are. So C2 tilde and C1 tilde must be equal to each other for this to equal 0, which means that our C2 tilde is exactly the same as what we had for C1 tilde, be just this -1/2 e to the, it would just be the same, exactly, these are equal to each other. So we have our C2 tilde. So we have our C1 tilde and C2 tilde, so we can go all the way back to our solution, which is this right here, with all the C1, 2, and C2 tilde plugged in. So maybe I'll just actually the C1 tilde and C2 tilde are the same. So this would essentially be like this -1/2 e to the pi plus 1. They have an e to the -t that's the same, so it'll be e to the -t that is out here. And then I'm just going ahead and saying, like, if you did plug in these values for C1 and C2, those would be the same, and then e to the -t are common, so we could have factored all that out and then been left with cosine of t plus sine of t. And then I'll just make this all black. And underline it in blue to be consistent with, so we have, I'll make it even put it in a box. So we have this right here. And then this is what we had previously for before it short-circuited. So I'm just gonna put little, so this is for t between 0 and before, and when it shorts out at pi. This one will be for t pi greater than pi, and then keeps going up to 2 pi. So we have success, there's no more C1s, there's no more C2s, there's no more C1 tildes, C2 tildes, none of that anymore, because we've found all the arbitrary constants. Before short circuits, you had to use the initial condition, which was this Q of 0 is equal to 0 and Q prime of 0 is equal to 0, which is basically this stuff right here. The C1 tilde and C2 tildes are not necessarily the same, and obviously we see that they're not the same as the negative half that we saw before. But for those, you'll use the continuity conditions like we did with mixtures. You can't have charge suddenly appear, current suddenly appear or disappear right when it short circuits. So when you graph this, I mean, I can write like, so your solution for Q as a function of time, which is the charge, how your charge evolves in the circuit, is now going to be is a piecewise function. The first piece is going to be this right here. And the second piece is going to be this right here. And it's going to be like this, and then you're just going to have this is for 0 to pi. And this is for pi on 2 pi. And this is like your Q2. This is your Q1. And if you graph this, this is Q. You'll see that when you're letting it initially start with 0 charge, 0 current, so you could think of it as like a horizontal tangent line here. And the battery is in the circuit will increase the charge on the capacitor. Then it short circuits. This point right here is like your pi, because it's between 2 and 4, and pi is 3.14. So it's going to short circuit right there, but you don't want like a discontinuity in the charge there. So it just basically the charge in the circuit will be whatever it was at that point. But because the battery shorted out, the charge in the capacitor would discharge. And it looks like it over discharges. If we were to graph this further, let's see if I can click on the graph and then find it. Okay. I don't know a lot of electrical engineering, so I don't know like what it means when it like goes below. Okay, so I cut this at 2 pi, but let's say if you made it go to 5 pi. So it looks like it short circuits, the discharges charge, and maybe over discharges, and then it will equilibrate to 0 charge. Somebody could ask their electrical engineering professor why it might dip below 0 for a moment and then return to equilibrium. So that's like a piecewise solution because you have something happening midway through. You have a short circuiting that happens in your circuit. It's going to require you to build an equation for before and after it short circuits, solve them separately. The first part is just solving the initial condition, using the initial conditions as normal. The second part requires you to use these continuity conditions. There's 2 now instead of 1 because it's a second order equation compared to the mixture problem. So you need 2 for 2 unknowns because C1 and C2 are your unknowns. You find those, and then you should be able to, if you were to graph it, notice that you have a function that is both smooth, both differentiable and continuous right at this point. Any questions? Okay. So that's just the last problem. It's a longer problem, but it covered all I really wanted to say for electrical circuits. We're going to move on to higher order equations. This is jumping back to 2.4, so it's kind of weird because we were just in 2.8, I believe. Yeah, 2.8 here, but we're going to try back up to 2.4 because that's where they actually start doing higher order equation. What is higher order equation? Higher order equations are equations that have more than like x double prime. So this has x quadruple prime. If you want to find the general, so this homogeneous, so we're going to do high order equations with homogeneous, so it's easier. And then we'll do non-homogeneous high order. So the zero on the right-hand side will not be zero anymore, but some other number. Oh yeah, and just in case if it's not clear, this was the blue graph, and then this was the red graph. But I think that was clear. So let's do the character. So let's think about like if we were to try to do this, what did we used to do? Let's go back. Let's just go all the way back to 2.4. Yeah, it's up here. What did we used to do? We used to do, so if you had like constant coefficient a double x double prime b, this was only up to x double prime. We used to say, okay, let's propose our solution form to be CE to the RT. And then we took the derivative of it and we took the second derivative of it and plugged it in. And then we noticed that if we want to look for non-trivial solutions, so when C is not equal to 0, then we must have had an R that satisfies AR squared plus BR plus C. That was what we used to do. The book, this is a screenshot. It turns out that a homogeneous linear constant coefficient differential always has at least one solution of the form this, or, CE to the RT in general. And I had said this back then. It doesn't say anything about the order. It just says homogeneous, linear, and constant coefficient. It could be not necessarily second order. And so I wrote down here, and this applies to second and any higher order homogeneous linear constant coefficient differential equation. At the time, you may have just not really picked up on that, but now is where I'm going to highlight that back then I said that this actually is true for regardless of whether it's second or third or fourth or fifth or seventh order, so long as it's homogeneous, linear, and constant coefficient. So let's go back and see if it satisfies those things. Go all the way down. So let's look at this, and we can see that it is homogeneous because it's 0. It's linear because all your x double prime, x quadruple prime appear linearly, which means to a power of 1. And it's constant coefficient because the coefficient of in front of x, this is 1, -5, and 4. So it satisfies all those things. So we are allowed to say that we can propose the solution to be x is equal to CE to the RT, like we did before. And then it's going to be like x prime is equal to R CE to the RT, because you're just using the chain rule. The R pops out. X double prime will be R squared CE to the RT. X triple prime will be R cubed CE to the, you see how like the chain rule is just popping out an R each time. And then X quadruple prime will equal R to the 4th CE to the RT. And then we're going to plug this in. The X quadruple prime will be this after you use this solution form. And then you're going to do a -5. X double prime is this one. And then +4 times just x. X is just this. Equals 0. Okay, you can factor out, like we did before, anything that's common. So the CE to the RT, CE to the RT, CE to, they're all common to all these. So CE to the RT is clearly common, leaving us with R to the 4th minus 5R squared plus 4 is equal to 0. Now, if we're interested in non-trivial solutions, so we'll just write the same thing. C cannot equal 0 if we're interested in non-trivial solutions. Because if you set C equal to 0, then your solution would be 0. X is equal to 0 after you set C equal to 0. And that will always satisfy any homogeneous equation, will always be satisfied by this x is equal to 0. Because if you took plugged in x is equal to 0 into this, that's 0. 0, double prime of 0 is 0, quadruple, yeah. But that's not what we want. We want non-zero. So we want so-called, that's called a trivial solution. We want to have non-trivial solutions. So that means that we want to make sure that this c here is not equal to 0, which means that the only thing that you could have if you're not allowing that to be 0 is to have what's inside of this parentheses here to equal 0. That's the only way that you can do it if you are looking for non-zero solutions. And this is well, we called it in the past our characteristic equation. We will still call it the characteristic equation, but it's a characteristic equation for this higher order equation. And then you'd factor this, so this actually factors to r squared minus 1, r squared minus 4 is equal to 0. So you'll have r squared is equal to 1, and you'll have r squared is equal to 4, which means that r is equal to plus or minus 1, and r is equal to plus or minus 2. That's like your two r's after this. There is a total of 4 r's. There's a 1, there's a -1, there's a +2, and a -2. And based on your understanding of the solution for these are distinct, they're all distinct real. What should be one homogeneous solution for sure? C1 e to the e to the t should be one of them. What is another one? Yeah, and another one. It's you want to probably 2t, yeah, 2t. And then c to the 4, e to the -2t. So it's the same pattern. They're all separate homogeneous solutions. You know, R for any of these would actually solve them. And then we proved before that the general homogeneous solution would just be a linear combination. So it would be just the sum of all the homogeneous solutions, where the coefficients may not necessarily be the same. They could be. I mean, if you apply some initial conditions, they may end up being some of them the same, but you don't assume that ahead of time. They turn out to be, that's fine, but you can't assume that ahead of time. So you have 4 arbitrary constants, and it's consistent with what we said before that the number of arbitrary constants is going to equal the order of your equation. Order of your differential equation is the highest derivative that shows up. So this is a 4th order equation. 4th order ODE. And you should see 4 arbitrary constants. When we had a 1st order differential equation, we just had C. We didn't even do C1 or C2 because there's only 1. That's because it's a 1st order equation, should only have 1 arbitrary constant. 2nd order equation has 2 arbitrary constants, C1 and C2. So if you're not getting the same amount of arbitrary constants as your order of your highest derivative that shows up in your equation, then you made a mistake. It doesn't have all the you wouldn't have a description of the full general solution if you missed one of them. And so if you're taking linear algebra, then the space of solutions for these differential equations has a basis, and the basis would be each of these, e to the t, e to the -t, e to the 2t, e to the -2t. We can show later would be linearly independent and would be a spanning basis for the entire solution space of this differential equation. And linear combinations of that would describe any solution in this space of solutions for this differential equation. But that's not important. I just you know, just a little bit. You don't have to have taken linear algebra, but we will touch on it a little bit. And so that's the solution for this. Now, you don't have to do all this. This is a pain, right? To do c to the RT, r squared, r to the fourth and all that. There's a pattern that is exactly what we saw before. When we see an equation, the r to the power on the r is the order of the derivative. Remember, like x double prime became r squared, x prime became r, and x just became the constant. Well, that still holds. So x quadruple prime is just r to the fourth. So you don't have to do all this, but that's where this is coming from. So you can build the characteristic equation quickly by just that observation. So here you have a third order equation, and the characteristic equation is simply r cubed minus 4r squared plus 5r minus 2 is equal to 0, right? So you can go immediately and just use that same idea that we had before. And for this one, it's going to be just it's all an algebra problem at this point. So you just have to find the r's that solve this cubic equation. And it turns out that the cubic equation is harder than this fourth degree equation, because it's hard to see what the roots of this would be. So you typically might try some easy numbers like r is equal to 0, or r is equal to 1, or r is equal to -1. And it turns out that if you plugged in r is equal to 1 into this, it'll be 1 cubed minus 4 times 1 squared plus 5 times 1 minus 2. And if you type this in your calculator, it'd be 1 minus 4 is -3, plus 5 is positive 2 minus 2. This is equal to 0. So r is equal to 1 is one of the roots. So r minus 1 is a factor that you can pull out. And we'll do, so if you have a cubic equation and you already know one of the roots, then you can do polynomial long division to find the other two roots, because you divide this factor out of the original. And we'll do that and get your other two roots. And then it's going to be like e to the one of them plus c2 e to the other one plus c3 to the other one will be your full general solution. But we'll do that next time.